Hey guys, back with some more probability, back with some more MIT OCW probability statistics. Let's do it. Let's just rename these guys. Okay. Okay. Oh yeah, I wanted that duplicate. Let's go just like blank. All right. So got this. No, not the solutions. I'll bring up the solutions. Over here on the side. Left blank. Get these side by side. Hold on, let me just get the blank on the right. This one. There we go. Alright. Cool. Dang, I don't want the solutions. What the heck? What are these? These are the solutions? No. Alright, but I do want the solutions up right here. Alright. So where did we leave off? Basically, here. Where's the thing? Writing pad's not working. Still not working. Let's go on. Dang. What is this thing? Remove, backup, restore. Is something wrong with my pen? Remove. Reset. Didn't do anything. Click the lock to make changes. Reset. Okay, there we go. I just have to gotta change these things again. How do I? Let's see. Wacom. Display settings. Okay. Tablet utility. That's this thing. What about the center? Oh, okay. I guess it's this center. Pen settings. mapping. Wanted to take up the full thing. Settings. Edit. Where was this? It's this, huh. I was able to do this before. What is this? Oh, okay, here we go. Screen area, just monitor 1, I think. No, just want monitor 2. Okay. Working now. We good. We back. Nice. All right. Cool. All right. So we had a diversion last time into, formalizing or framing this thing as a probabilistic experiment where we define the, let's get this down here. All right. Where we defined the sample space as, it's almost like, just to be fancy, we defined it as these z. You know how you do like you say like the real numbers, but then you can say like R5, which is the like real numbers of I don't know. It's like the reals crossed with the reals crossed with the reals, like to 5. I'm trying to think if we can define our thing like that. Like we say like Z5, not 5. But so yeah, we're talking about omega, and what do the elements of omega look like? That it's almost like it's almost like they're like Z Zn, because we got n people. Yeah. So for instance, if n is equal to 3, we've got elements like 1, 2, 3. And 1, 2, 3 is an element of Z3. Z3. Okay. So I guess we could say then that omega is a subset of Z3 something. Yeah, could say that. So yeah, we had this diversion last time where we were kind of looking at omega, and we were kind of trying to figure out like what the elements of omega even were, what kind of shape are they? And to give some just like shape, we'll say, okay, they're a subset of Zn, I guess. Because like before we were kind of thinking that omega is a subset of just like Z, they're just, it's almost like we just do an experiment and we get a 1. You pick hat 1. Or you do an experiment and you get 3, like you picked hat 3. But in order for this kind of sequential kind of probabilistic experiment for us to be able to actually use the machinery of probability theory, like conditional probabilities, we needed to define the sample space in terms of basically tuples, where every element in the tuple was like the nth person drawing the hat. So if we have like 3 people, then the outcome of the experiment where person 1 gets hat 1, person 2 gets hat 2, and person 3 gets hat 3 is like this outcome right here. And for this experiment, like these are the only outcomes. You can't get like an outcome of 1 for this experiment. This experiment has multiple steps and multiple stages to it. So, given that, maybe let's redo question 1 with that understanding. So, what is the probability that every person gets his or her hat back? Well, let's see. Basically, yeah. If we think of like n is equal to 3, for instance, and all the outcomes are like 1, 2, 3, like 1, 3, 2, 2, 1, 3, and we just kind of keep on going. So if like this is our sample space, and literally like this is the only outcome that like this is the only outcome that would correspond to the event that everyone gets his or her hat back. So then like the probability that every person gets his or her hat back. It's really like the probability that we get 1, 2, 3 in this case over the, well, I guess it's like the probability of omega, but I really want to, yeah, but since this is just a counting problem, every outcome is equally likely. This is just equal to the cardinality of 1, 2, 3 over the cardinality of omega. And yeah, so this is just equal to 1 over the cardinality of omega. And so the only thing we need to determine in this case is, yeah, what's the size of omega? Like how many possible outcomes are there? So that's where last time so we're asking, yeah, what's the cardinality of omega? And so we kind of thought about how these outcomes get generated, like 1, 2, 3, for example. And so we kind of think about like how many different possible things could happen. And I guess if these events were like independent, it would actually be simple to kind of just think like, oh, there's like n element. I don't know. Actually, I don't even want to think that way. I don't even want to take that for granted. It's like, so how do we actually generate this thing? Well, we think of a sequential probabilistic experiment where we pick the first hat. So let's say n is equal to 3 here. So we pick the first hat. We could either get hat 1, 2, or 3. And then Yeah. If we had replacement, if we just like pick the hat and then we just like put the hat back, we could get, 1, 2, 3 again. And we could get 1, 2, 3. And we could get 1, 2, 3. But that's not the nature of this probabilistic experiment. We, yeah, each person just picks their hat at random. Like it doesn't mention anything about replacement. So basically, once hat 1 gets picked, it's gone, and you can only pick hat 2 and hat 3 now. And here, if we picked hat 2, hat 1 is gone, so we could do 1 or 3. And here we pick 3, so 3 is gone, so we can do 2 or 3 in this case. Yeah, now, and like in this case, we picked hat 1 or 2, they're both gone, so we could only get 3. In this one, we could only get 2. In this one, we could only get 3. Only get 1 here. 3, 2, 1. Oh, messed up on this last one, I guess. 3, 1, and 2. So here, 3 and 1 are gone, so we can only get 2. 3 and 2 are gone, so we can only get 1. Okay. So each of these, branches corresponds to an outcome of this probabilistic experiment. It's an element of omega. So we just need to count up the number of leaves essentially here. So we basically like count up, how many leaves are there. And we can kind of do that by counting up the number of leaves at each step, kind of. Like at step 1, there were n is equal to 3. And then for each of those, there was 2 possible outcomes. So yeah, there's basically like 3 potential like outcomes for each like node. And then here we say for each node there are 2 potential outcomes, and here for each node there's just 1. And we went more into this last time, but we could just like multiply these together. This is like 3 times 2 times 1. 3 factorial, 6 in this case. So yeah, that's the only addition we really made here, just thinking about like sample space. So anyway, all right, what's the probability? Yeah, okay, 1 over n factorial, it's fine. All right, the first m persons who picked their own hats get their own hat back. So yeah, I'm kind of thinking about this in 2 ways now. It's almost a bit more intuitive to think about it in terms of the tuples. So I mean, say for instance, n is equal to 4 and m is equal to 2. Then we know our sample space omega looks like whatever, and it's got elements like 1, 2, da da da. It's got elements like 1, 2, da da da. And we basically just want to, like count up the number of elements that start with 1, 2 in this case. Like the first 2 people get their hat back. So you basically need to count up how many elements start with 1, 2. And how do we kind of do that, or how do we think about that? It's like, I don't know, if like, so say n is equal to 4, then how many elements are there of 1, 2? So we kind of fix these. 1 and 2 are gone. Um, so two are gone. So there's a spot here where we could get, I guess we could get 3 or 4. So there's 2 remaining here, and then there's only 1 remaining here. I mean, so it's basically like, I guess there's only like 2. There's only 2, so it's like 1, 2, and we could get 3 and 4, or we could get 4 and 3. And I guess like the other way to think about it is in terms of the sequential decision process. So instead of doing the full tree before, where we could pick whatever for 1 and whatever for 2, like we, I guess like the outcome of the first thing is fixed at 1, the outcome of the second thing is fixed at 2, and then here for this third thing, we could get 3 or we could get 4. Could get 3 or we could get 4. And here, if we get 3, then we have to get 4. And if we get 4, we have to get 3. So basically, there's only 2 here. Yeah. So it's a probability that the first n persons get their own hat back. So how do I want to do this? Like, you could say, oh, yeah, no, that is one way to think about it, where it's like, yeah, we're just counting up like the number of instances of those tuples. Yeah, over so the number of those tuples is like, I guess I don't know, it's almost like we like fix the first like m, and then the n minus m remaining are kind of like variable things. So is that, I just want to make sure that's true. Like, so we're not off by 1. So say n is equal to 5 and m is equal to 2. Then we fix the first 2 things, and 5 minus 2 is 3. So the last 3 are variable. So by this point, how many hats are left? There's n minus m hats remaining. And the number of permutations of those is basically n minus m factorial. So we're basically asking how many of these are there? And like the answer is n minus m factorial, because we like we fix the first m, and then we like look at all the possible like remaining permutations, I guess. So I guess the answer would just be n minus m factorial over n factorial. Like that seems like what the answer is. Let's see. Yeah, n minus m. So consider the sample space. Probability event with, yeah. This is how many ways there are to distribute the remaining n minus m hats after the first m is assigned to their owners. Okay, that's good. Okay. So now part C. Let's see. Everyone among the first m persons to pick up their hats gets a hat belonging to one of the last m persons to pick up their hats. Okay. The last m. So if we kind of think about our thing, we're kind of like chunking it up into like 3 things. This is like the first m. This is like the last m. These look like mustaches. So everyone in the first m gets a hat belonging to the last m. So basically it's like, I don't know, let's say n is equal to 7 and m is equal to 3. So this person, there's basically like 1 in 7 chance for this guy times a 1 in 6 chance for this guy times 1 in 5 chance for this guy. So these hats are kind of like going away. And now once these guys get here, I don't know, can't just say now like, okay, yeah, it's like there's 7 hats, there's 6 hats, there's 5 hats, and now there's 2 people. There's kind of like n minus 2, like n minus 2 times n people in the middle. And basically we need it to be the case that these people don't pick any of the last m hats. So there's basically like 4 hats remaining, and this guy like has to pick, like can pick 2 out of 4, like 2 out of 4 of them are good. And now this guy like has to pick the last. There's only 1 remaining where it's, wait, so basically in the outcome that we want, these guys go and they pick all the hats from here. So they're gone. Now these guys have to pick basically like their own hats from here. So now like these are all gone. And now these guys have, like, there's only 2, like in order to get the outcome we want, the only hats that would be remaining are like these. So there's only 2 hats remaining. And so, I mean, like this guy's basically got like 100, like 2 of the hats are good that he wants, and there's only 2 remaining. And then, this guy here, there's only 1 hat remaining, and it's like definitely good by definition. So basically this kind of thing here. So there's kind of like an n factorial that gets cut off here, and then these guys have to do this, and then so it's basically equal to like the probability that the first m thing happens times it's almost like it's like the probability of like the left thing times the probability of the middle thing times the probability of the right thing happening. And so, yeah, basically like what's the probability of the first m thing happening? That's basically 1 over, what is this number here? It's n minus m is 4. So it's basically like, this thing is basically n factorial over n minus m factorial here. I guess, so it's like 1 over that times, now this is like, so this number up here, like this number here is going to be some kind of factorial. It's going to be like, so how many elements are here? Yeah, there's n minus 2m. So it's like n minus 2m factorial over 4 times 3. I guess it's going to be like n minus m. It's going to be like n minus m factorial, but then you're going to divide that by n minus m divided by how many, you want to cut it off. It's gonna be like n minus m minus how many guys are in here. I think it's like n minus 2m. Basically like this factorial. And then you basically like multiply by 1. So yeah, it's almost like kind of simplifying this. Like this thing flips, so it'd be n minus m factorial over n factorial times this thing divided by, which is like basically times, is basically like n minus 2m factorial times, how do we simplify this? I guess like these guys would cancel out, negative m plus 2m. I guess that would just be m factorial times n minus m factorial. I guess like it looks like these would cancel out. So the answer would be like n minus 2m, whoops. N minus 2m factorial times m factorial over n factorial. That seems wrong that the n factorial would be on the bottom. 1 divided by this is equal to this thing flipped. Yeah. Oh, wait. So what were we doing? Oh, we were, oh yeah, I think this should have been like 1 over this thing, because we should be multiplying probabilities. Anyway, I don't really care about getting the algebra 100% right. I think it's basically going to be like an m factorial and n factorial and n minus 2m thing in there somewhere. Yeah, m factorial, n minus m factorial. Wait, did we get that? N minus 2m. Yeah. We got close. We had n minus 2m, but this is just n minus m. That's okay. I feel like we went through the important part. So everyone among the first m persons to pick up their hats gets a hat. Yeah. Okay. There are m factorial ways to distribute. Yeah, I feel like we should understand it in this way. m hats along the first m persons, and that many ways to distribute the. I feel like that's a better way to go about it. Yeah, let's think of it in terms of counting, because we just did the logic where we multiply probabilities, but let's just think in terms of counts. So basically, all right, let's define like event C as being like part C. And so we'll say like the probability that C happens is equal to the number of elements in C over the number of elements of omega. So we know this is equal to n factorial, but we don't know what this is equal to. So what is this equal to? Like the number, yeah, we kind of think about like all the different ways that we could make this happen. So yeah, the solution was saying that basically looking at the first m and the last m, and then this is n minus 2m here. Just not gonna put that. So these guys are kind of weird. So it's like how many ways are there? If we think about like how many things of this form are there going to be, then we got to think like how many ways could this happen? And he was saying that there should be m factorial ways for this first thing to happen, which is true. It's like, let's just take these m hats and distribute them over here. So yeah, there is m factorial ways for that to happen. So now m hats are gone. So we have n minus m hats left. And so there's n minus m hats left, but there's only, but we only want to distribute like this middle bunch against itself. So this is the total number of hats remaining, but we can only choose, I don't know, like let's do a concrete example. Like let's say n is equal to 7 and m is equal to maybe let's do like 8 and 3. So in this case, there's 3. In this case, there's 3. And here there's 2. So we basically started with 8. N minus m is equal to 8 minus 2. 8 minus 3. So there's 5 hats remaining at this point. But if we sort of like started with 8 and we like subtracted 3 away from the left and subtracted 3 away from the right, it's like 8 minus 6. There's only 2 hats that we can choose from here. So there's 5 hats remaining, but n minus 2m is equal to 2 hats to choose from. So is this 5 choose 2? Is this 5? Is this 5 choose 2? Let's just think. Basically, if we line these hats up, we have like hat 1, 2, 3, 4, 5, 6, 7, 8. Okay. So let's say that, yeah, 6, 7, and 8 are gone because we assigned them to the first guys here. And so these hats are remaining. So here, we have like 1, 2, 3, 4, and 5, but we can only choose 2. Yeah, we've only got 2 remaining. I guess it's really just like the number of ways that you can permute n minus 2m. I mean, that would just be n minus 2m factorial. Yeah, and it'd just be like times 1. So I feel like the number would be m factorial. And then so for each of these, you can do this. So it's n minus 2m factorial. Well, n minus 2m factorial. And then, okay, but now you do need to say, all right, like now how many are remaining here? And it's like, how many of these can you permute basically? So this should be, so there's still like m factorial ways to permute those. And this is just over n factorial. So I feel like that's that's like kind of the answer. Yeah, how many ways? Because it's like you permute all these guys like n factorial ways, and then here you permute these guys n minus 2m factorial ways, and then you can still permute these guys m factorial ways. So that's how many there are. And then you just divide that by n factorial. So I'm just wondering, what happens if you have m factorial over n factorial? Like, can you just write that as, I mean, like all these terms would like cancel out up here. So I think that would just be 1 over n minus m factorial. Because like if you have 5 and 2, you have like 5, 4, 3, 2, 1, and then m is just like, I don't know, say m is 3, 2, 1. So wait, oh, we said m over n factorial. So it'd be like 3 times 2 times 1 over 5 times 5 times 4 times 3 times 2. So the m factorial would cancel out, and no, okay, that's not right. You can't just do n minus m factorial. No, this is basically like as good as you can get it. Yeah, okay. So I feel like that's wrong. Yeah, like the double m factorial. Well, so he got the full answer. Like, okay, so I had m factorial times m factorial. It's interesting to like write it like you could write it like m factorial squared times n minus 2m factorial. Interesting. Yeah. Oh well. That's okay. Okay. Now In addition, assume in addition, every hat thrown in the box have probability of P of getting dirty. What is the probability that? So let's see. All right. Getting dirty. The probability that the first M persons will pick up clean hats. So you kind of toss the hat in, and it's like it gets dirty with P and then stays clean. 1 minus P. The first M persons will pick up clean hats. So yeah, I think this seems kind of simple. So it's just like from 1 up to 2 up to M. It seems like to have them all pick up clean hats, it's like this has got to be 1 minus P. Probably 1 minus P, this will happen, times 1 minus P, 1 minus P, times 1 minus P. Seems like that's 1 minus P to the M. Seems that's pretty simple. Yeah, 1 minus P to the M. Probability of a given person, 1 minus P, independence, probability, yeah, 1 minus P to the M. Because if they weren't independent, it's like, oh yeah, okay, this is cool. So we can think of omega again as kind of like setting up our sample space. So I guess it'd be like so it could either be dirty or clean to the n, I guess. So if n was 3, we could be like, we could have an outcome where it's like dirty, clean, like this. My lips are really like dry. Brutal. I'm gonna like lick my lips in front of the screen. It's like weird. Yeah, and so basically like, yeah, the first M persons will pick up clean hats. So again, like we basically want it to be like, if n was 3, then we could be like, these are all the outcomes. We could have like clean, but clean hats, yeah. Clean, dirty. Instead of C and D, I'm gonna do it like, all right, clean. We could do clean, dirty. We could do clean, dirty, clean, dirty. We have dirty, clean, dirty, and dirty, clean, like this. So there should be 2 times 2 times 2, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's good. So basically, like asking what's the probability that, what's the probability of D? What's the probability of part D happening? And that's just equal to, it's going to be the count of D over the count of omega, and the count of D where they're all, actually we can't just go by this count thing anymore, because these have different probabilities of clean hats. This is like the probability of getting dirty. So this is like 1 minus p cubed. This is like 1 minus p squared times p. Yeah, so these are different outcomes. So you basically have to add them up now. Like you basically have to say it's equal to doing a sum now where for all the D's in this set, I guess it'd be like the probability of D. Yeah, it's just the probability. We're just summing up all the probabilities. So it's just this one, I guess. Yep. And there's only one outcome, so yeah, that's fine. Okay. So that's fine. So now what's the probability that exactly M persons will pick up clean hats? So we have N people, and we want to find out probability that M people pick up clean hats. So it's like we have N people, and we want to choose M of them to pick up clean hats. Okay, so what's the probability of this? So if I just said, all right, so like we ran this experiment and we got an outcome. It's like little omega, I think, is this. And we got an outcome. So you say, and I tell you something about the outcome. I say, all right, W has M clean hats. And so like, what's the probability of this individual thing happening? Well, like we don't know the order, but we know that there are M clean hats. So there's there's M times 1 minus P. Wait, no, there's like, so there's like 1 minus P times 1 minus P times 1 minus P. So we know that there's like M. Maybe instead of jumping to this, let's like take one more step before that. So let's say that N is 5 and M is 2. So we run the experiment and we get an outcome. And we say W has, not even say like W has Okay, we know this about W, but let's just say we got the outcome. You know, clean, dirty, dirty, clean, dirty, like that. Like this is the outcome that we got. So now we say, what's the probability of this outcome? Well, the probability of this individual one is clean. Says it gets dirty with probability P. So like this is like 1 minus P times dirty times 1 minus P times dirty. Gets dirty. This is equal to 1 minus P squared times P cubed, which is equal to 1 minus P to the M, it's P to the N. Okay. So that's the probability of this particular W. But if we want to know all the W, which has M clean hats, it's just, we just multiply this. We just multiply this. Multiply this by cardinality of D. Cardinality of D, how many ways are there to choose M clean hats from N things? I guess it's N choose M, 1 minus B to the N times B to the N. Seems like that's right. N choose M. Every group G of M persons defines the event. The heck? It's a weird way to start it off. Every group of N persons defines the event. The heck? Everyone from G picks. This is like a riddle. What the? This is like this sentence is false, like thing. Every group defines the event. Everyone, not everyone. This is weird. I don't even understand that, and I don't even know if I want to ask ChatGPT. I don't think I really care that much. All right. So let's look at this one. Let's look at the next one. Might take a break now, but let's just look at it. All right. Alice plays the following game. Inside of my mouth is itchy. Yeah, I'm gonna take a break before I do this next one. It's like a card thing. All right, thanks guys. See you next time.